There are versions of, or there is a version, I should say, of compensation for subtraction and division as well. These work a little bit differently because, again, the associative property only applies to multiplication and addition. It doesn't apply to subtraction and division. So we have a different form of compensation, and the justification is a little bit different as well. Nevertheless, we can use a mental math technique to solve subtraction problems like the following. Consider the problem 303 minus 96. Now, if our thought process in general is based on taking a problem that is hard to solve mentally and turning it into an equivalent problem that is easier to solve mentally, what makes this problem difficult is that, again, we have to regroup in two place values. Okay? So we want to turn this problem into an equivalent problem in which we don't have to regroup in any place values, because that's going to be an easier problem to solve mentally. Okay? So the steps here are a little bit different than they were with addition. With addition, it didn't really matter which number we choose to work with first to turn into a nice number. With subtraction, it does matter, and here's the reason why. 303, both 303 and 96 are kind of close to nice numbers. 303 is really close to 300, which is a nice number, easy to work with, and 96 is really close to 100, nice number, easy to work with. But what if we were to change the 303 into 300? Regardless of how we end up compensating the 96, we are going to guarantee that we are going to have to regroup when we subtract now. Because if our first number, called the minuend, ends in a bunch of zeros, then we are definitely going to have to regroup, right? So we don't want to change the minuend, or the first number in a subtraction problem, into a nice number, because then we will guarantee that we have to regroup, and that's what we want to avoid. Okay? So our process for subtraction is going to be completely based on changing the second number, the subtrahend, into a nice number, a number that ends in a bunch of zeros. In this case, the 96, we want to change to 100. Okay? So we are going to change 303 minus 96 into a problem where we're going to subtract 100. And I'm going to leave a blank here, because the question now becomes, what do I have to do to that 303? I have to compensate somehow. Right? I changed the 96, so I'm going to have to change the 303 somehow in order for my new problem to have the same answer as my old problem. The question is, what do I do? Now, with addition, remember we did the opposite to both numbers. If I added to one number, I had to subtract from the other number to compensate. How does it work with subtraction? Well, a diagram can help us figure out the correct way to compensate. So if we think of 303 minus 96 from a comparison subtraction perspective, then we could draw the following bar diagram. So if we think of 303 minus 96 from a comparison perspective, then the question is, how much longer is the 303 bar than the 96 bar? How much bigger is 303 than 96? So the answer to this question is the difference in the lengths of the bars. Okay? So this diagram, as we saw when we discussed interpretations of subtraction, this diagram can illustrate 303 minus 96 from a comparison interpretation. Now, what did I end up doing in my mental math procedure? What I ended up doing was I added 4 to that 96, right? So if I add 4 to the 96, that makes this bar longer by 4. So the question now is, what do I have to do to the 303 in order for the new problem to have exactly the same answer as the old problem? Well, what that means is that the question mark has to still represent the difference in the lengths of the new bars. And you can see that the only way the question mark is going to represent the lengths, the difference in the lengths of the new bars, is if I also add 4 to the 303. The bars that I've created now are 307 minus 100. The difference in these bars is exactly the same as the difference in the 303 minus 96. Okay, so for this reason, it turns out that to compensate in a subtraction problem, I actually have to do the same thing to both numbers. So for example, if I added 4 to 96 to get 100, I'm going to have to add 4 to the 303 to obtain, in this case, 307. So once we've got this sorted out, we see that, again, 307 minus 100, a much easier mental problem than 303 minus 96. We get our 207, And that is the general process for compensation with subtraction. So again, it differs slightly than the process for multiplication and addition in that it actually matters which number we decide to change at the outset. We want to change the subtrahend, the second number, into a nice number that ends in as many zeros as possible. And then the way that we compensate is different than it was with addition and multiplication. With addition and multiplication, whatever we did to one number, we did the opposite to the other. In this case with subtraction, whatever we do to one number, we have to do exactly the same to the other. Okay, our last operation is division. There is a version of compensation for division. And the process, again, resembles what we just did for subtraction. So as an example, what if we have the problem 375 divided by 5? Again, not that difficult of a mental problem. However, to solve this problem, we might actually have to carry out the division algorithm, and we want to avoid that whenever possible. Again, our thought process is based on, is it easier to divide by a nice number, a number that ends in a lot of zeros or as many as possible, or is it easier to have that type of number, a nice number, as a divisor? Well, place value tells us that it is very easy to divide by a number that has a lot of zeros in it. So if we change this 5 into, let's say, a 10, it's easier to divide by 10 than it is to divide by 5 mentally, then our question is similar to the question we had for subtraction. How do we compensate? What do we have to do to this 375 to maintain the quotient, to create a problem that is equivalent to the problem we started with? So if we start with 375 divided by 5, and we change this 5 into a 10 so that we're now dividing by 10, the question is, what do we have to do to the 375? Okay. We can use another diagram to illustrate what is actually needed here. If we think about 375 divided by 5 from a measurement division perspective, recall our discussion of measurement division. The question that's being asked in this case is 375 is how many 5s, or how many 5s make 375? So what have we done in going from our original problem to our new problem? What we've done is we've doubled the divisor, right? We've made the divisor twice as big. So in our bar diagram, if we made the divisor twice as big, what would we have to do to the entire bar to make the same number of these pieces fit in the bar as the same number of 5s that fit in the 375? And clearly we would need to double the length of the entire bar. So whatever we do to the divisor, we must do the same to the dividend. So the same number of 5s that are going to fit into 375 is the number of 10s that are going to fit into 750. So just like with subtraction, whatever is done to one number arithmetically must be done to the other. If we double this 5 to create 10, we need to double 375 to create 750. Again, 750 divided by 10 is a much easier mental problem than is 375 divided by 5. And that's how we obtain our answer of 75. So compensation is one of many mental math techniques. With addition and subtraction problems, it is a very powerful technique. With division and multiplication problems, we've seen examples where it works, but the examples had to be structured in a very particular way, and it's going to turn out that there are many other techniques that work for even these examples of division and multiplication, which we'll see in another clip.